Hello, I'm Igor Kuralenok from Yandex Cloud. I'm responsible for machine learning there. This is the topic of my presentation. I'm going to speak about how machine learning is embedded into clouds. And to make sure that we are talking about the actual subject, let's just start with the implementation, development of such solutions. I think this process is quite complicated. It's made up of different processes, and it usually starts with the development of a prototype. In the analytics, data analytics, we create some prototypes. We take some data and we check and verify the concepts of whether we can make a prediction about issuing a credit line for an individual or not, and then just stipulate its behavior in real time, understanding whether it has any value at all. Once we have developed the prototype, we have to move towards what we can utilize, because a prototype gets quite difficult in terms of utilization. And we come up with a solution which can actually be installed into a different type of a production. Once we have done this rationalization, we move to the actual production stage, where we're trying to deploy it into a stack and use it as a solution. In practice, it normally looks like this. We start with the creation of a prototype created in Jupyter on a desktop PC or a laptop by our data scientist. Once we understand that this prototype is a nice one, we run a live experiment with the live data, and we check out that we have predicted the future in real life, which is kind of good. Once we have conducted the experiment, we put it into the service. And it's quite a complex journey, and there are quite a lot of things that can go wrong in this journey. For example, the prototype data and experimental data can be quite different from the production data, and most of you have noted that as well. Lots of times the data uploads are done by a data engineer, and the data engineer sometimes does not quite comprehend the subtleties related to statistical processing of the data they upload, and sometimes they can make mistakes there. At the front time, people will be seeing the actual data. This is where all of our solution can go wrong, but that's not the only problem. The model itself can prove to be a problem as well. We can create a normalization of one kind, and in production something can go wrong, and it can be changed as well. And our model can also be functioning in a wrong way and not the way we measured. It proves to be a significant problem because we have different contours here, the one being the analytics contour, the other one being the production contour. Basically, what we would like to come up with is the idea, okay, let us try and merge them, let us try and combine them. Combine the production contour and the development contour, thus eliminating the mistakes that we have just demonstrated. For example, we can include the data selection into the prototype creation mode, and we can utilize the model we created for early adoption with some additional capacities added. We can use it in production just to understand whether it can be considered a reliable one or not. This idea is very, very obvious, but however, there are kind of a few obstacles on the way. Let's just try to move from production to development. Let's just try and put this production tasks to the development stage, and people do that quite frequently. For example, we have this Databricks product, which starts from the existing environment. Databricks is well known with Spark, and they start with the Spark production environment. In order to input these development tasks, what they come up with is the environment that some of the tasks can be resolved in Spark and some other tasks will be added to Spark. And adding this to Spark proves to be yet another problem, because nothing is that obvious and not too simple, and not all of the tasks would squeeze into this map queues paradigm. In Yandex, we've already tried this, and we have quite sizable systems tackling machine learning tasks. And we have the MapReduce system for Yandex, where we have just applied that approach. What we've been trying is to squeeze all of the tasks into the MapReduce system. We are running a risk here. Besides, not all of the tasks would squeeze into the MapReduce paradigm. Like I said, I was hearing a story about Horovod and the ring, which is not quite MapReduce. And in order to squeeze that ring into MapReduce, we have to pull off quite a lot and put a lot of effort into it. And also dedicating the tasks is getting difficult because there are dozens and dozens of tasks coming from MapReduce, because the tasks would split into tiny ones related to the data and very chunky ones, or like, for example, related to a very lengthy education and learning dedicated to just one GPU machine learning machine. Therefore, the tasks turn out to be very, very heterogeneous, and it proves to be a great challenge in our landscape. Also, there are some kind of difficulties arising because we'll have to isolate the tasks from one another, and the latency system increases during development. Those were fundamental problems. And this year, Yandex Cloud has been offering DataSphere's product. This product is tackling yet another combination task when we combine the development and production, but we did do it in a different fashion. What we try to do is to turn the developers' tasks into something which is very, very close to production. For this, first of all, we'll have to represent the development process, and then we need to conduct some steps in this process and change them and make sure that they have properties that the production has. For example, it's very important to use isolation's principle here. Isolation is very, very important. This model creation process can be imagined like, for example, we get this programmed with the Jupyter notebook and work as a developer. And each step of ours as a developer should be isolated in different ways. The results of each step would have to be some kind of a new variable. And these variables are stored inside the environment, our development environment, and we need to isolate these results from the system itself. Thus, from the interpreter, Python interpreter, then we'll have to make sure that the execution of one cell does not somehow affect the execution of another one, but the state transformations. It does not always happen like this. For example, it may so happen that something changes in the file system or something else which does not pass the state, which we'll have to eliminate. And number three, which is user isolation. Users should not be seeing one another. And there are many other things which are done there, and they are also interesting, but these have been the most important ones. So how do we achieve all that? Let's just take a look at the development framework and how it's changing. As a basis, we take a Jupyter interface. So why should we scare people? People see us with Jupyter base and they think that we provide notebooks as a service. No, it is actually the only thing which makes us similar to Jupyter. All the rest is done in our multi-tenant distributed system. And the entry point is the coordinator. The coordinator gets the tasks to execute the cells. The coordinator coordinates. They coordinate the variables in the systems, but these variables are stored in the data storage. To run that, we use multiple machines, and we use the selected ones appropriate for each type of calculation. All of these changes go through one single point, and what we need to make sure that this whole process is the flow of these variable states, and we get a very good quality of going back to each development starting point, which is pretty good, I think. What we have here is the new vague word, serverless. Serverless is when we run each cell with serverless mode, and we put the computing mode only when we do something. Like, for example, our partners say that approximately 60% of the time the developer does not spend calculating, but they spend inventing something, coming up with something, looking into a screen. And number two, for some tasks, we require computational power. For example, if we would like to train a huge model, what we need to have, we need to have resources, computing resources like GPU or an entire GPU cluster. That's on the one hand. On the other hand, if we make a plot, if we make a bar chart, we can utilize something less less potent with this serverless approach. We come up with a very interesting system, but not the only one. What we do is we have the distributed cell execution. Excellent. When we have done something which can be repeated, that's one good thing. Another thing, it is something that we can run in parallel. Like, for example, we can run it in parallel on more than one machine. Excellent. This is our way to production. We can basically say bluntly, all right, we have these 100 machines which will run this particular cell. Excellent. So we will be able to get at least 100 results in the same short span of time. And as far as the repetition is concerned, the results will be just exactly the same, which is good. And also this allocated execution provides us with different other properties. Like, for example, we can take the money only for the time spent on computing. You just pay as you go, you apply pay-as-you-go calculation model. You pay as you pay for the time spent on cell execution. That minimal amount of time just takes fractions of a second in most cases, sometimes even less. Number two, we separate the state from the interpreter, and we basically limit it with only those libraries that are capable for that. Luckily, we work with Python, and Python as a language has this serialization as the embedded component. So we have very few exceptions, and if we have such exceptions, we fix them, as we see them. And we don't have this access to hardware, which is a good thing, and to which we have started getting used to. Then, yet, we have this uniform data storage, which is a plus, and which is available from different sources, and we store this whole computing history in there. Like, for example, if we've made a wrong step, once we've done it, we can roll back to the version which was still intact. Or, for example, we select some kind of a parameter and we run it on a few machines. We run this computational algorithm on a few machines, and we run it not consecutively, but we run it in parallel, saving time. We also have a production framework apart from development, and production is split into steps. Like, for example, we have processes. People sometimes call it ETL. We split it into different steps, and by making these steps, we are joining them into a single graph, and we run them repeatedly. And sometimes we just do it in a runtime mode with a microservice architecture. We split this into stages. So we split service into stages. Services are joined through the same bus or data storage, and we have a kind of a graph, execution graph, which can be allocated out of that system, singled out of that system. And we can modify that for development. We can modify the scheme for development so that we can put ETL processes and API in there. The cells can be turned into a microservice. It accepts JSON. This is the A, which is variable, which is 10, and variable B with something else related to it, and then the cell runs it, and it defines a microservice, the prediction result, and it's put into a C variable. C variable is a result. We got the inbound JSON, outbound JSON. Altogether, it defines a microservice. It's repeatable, and we can use it as an ETL scenario and API scenario. And we can join such cells not only in one notebook. We can have our partners customize this model like we very often do in SpeechKit, which we use for voice recognition. And if we check out our voice recognition function, it has a language model embedded, which can be very different from one scenario to the other. With what we have a service which we pull out from acoustics notebook, where acoustic model is applied and utilized, where language models are applied and recognition normalization is conducted, etc. Our partner can take and utilize some of these cells we have developed for the model, add their own specific model, and come up with a new graph which will execute recognition API. Therefore, we demonstrate this flexible approach, and we can use these pipelines multiple times for different purposes, so that we can customize them for pipelines required for other cases. Therefore, we come up with DataSphere. DataSphere is not just required for the development and machine learning. What we would like to do is to make sure that it can be utilized right there. The actual model, like if you check Yandex Cloud right now, you'll be able to work with the utilization contour. The production contour will come up in the first quarter 2021. But some of the previews will be demonstrated even earlier, at earlier stages. Please join us for that service. And I think we'll be able to demonstrate the actual development and the actual production, how they can meet one another, how we can reduce time to market, reduce time from development to production. We're back with the sound, right? Is the question, two questions actually. It's a long one. Would you say that cloud models of machine learning, can they expect crisis? And if we have AI in each device and they will communicate with one another in cloud, will there be any problem of data transmission? Data transmission channels these days are not are just improving. They're not going back, they're going forward. We've all heard about these 5G talks, and our devices are getting closer to one another. And I think the computations that can be done run on the device, like for example the spotter for Marusia, are done there. The bigger, the better the quality. The bigger and the more powerful the piece of hardware, the better the quality. The high quality models will still be running on cloud, especially with the improved data communication links. Yes, I agree that some of the work will be done by the devices, but on the other hand, high quality, complicated and complex models will run on a cloud, so they will be coexisting anyway.